Yes. In last class, I have described about the equilibrium points between two charges which have the same nature, that is either positive, either negative. Here I am going to describe the equilibrium points of two different nature charges. Suppose one is positive and another is negative. See here. C, not to be Q, not to be this. This is our Q1, this is our Q. Here, this is our Q1 and this is our Q2. One is positive, another is negative. So, if they both are positive, in that case, we have equilibrium point somewhere in between them. But if they two are opposite in nature, in that case, our equilibrium point is not in between them. Let's check where we get the equilibrium point.
Write Q2 a little closer to you. It has been written on the spot. The reflection of this bulb.
Okay.
Yeah. Go a little lower towards you.
Don't miss people at the end.
Not that side. This side. This side. Yeah, closer to minus. Yeah.
See. So there are three spots. One is A, another is B, and the third is C here. So if we need to find equilibrium points here, so at A, I need to put a test charge, that is positive Q0. So determine the forces and the direction of forces. What we get? Q1 is positive. So on Q0, the force will be repulsive and it will be in this direction. That is FA1. And at Q0, force will be attracted by Q2 charge because it is positive. So this force is also in this direction. So this. So can you say that FA2 or FA1 may cancel each other or may not? No, they will not cancel each other because they are directed towards the same line. So A is not an equilibrium point. So our conclusion is equals to A is not an equilibrium point. So this concludes us that we don't get any equilibrium point in between charges Q1 and Q2. Now check on B. Suppose put a Q0 here. So force by Q1 at this point Q0 is in this direction. That will be, sorry, not in this direction, but the force by Q0 on Q0 is in this direction. That is FB1. And by Q2 is in this direction. Let's see here, what happened? Here, force applied by Q1 over Q0 will be repulsive, so this is away from the charge, that is FB1, means force over the charge Q0 at B by the charge Q1, that is FB1. And the force by Q2 at this Q0 is attractive because it is negative and it is positive, so it attracts itself towards itself. So the direction of this force is FB2 is in this direction. And here, if these two magnitudes are equal, then this might be our equilibrium points because the forces are opposite in direction, so they may cancel. If they cancel, then it will be our equilibrium points. So we can say that B may be our equilibrium point. Let's check C. What happens to C? If I'm putting the same test charge at Q at C, force by Q2 is attractive. See here, after putting Q0 at this point on C, what do we notice? That the force by Q1 on C, on the charge at point C, that is FC1, and it will be repulsive because it is positive, they repel each other. So the force is directed away from here. Similarly, the force applied by Q2 on this Q0 is attractive because it's negative, so it will attract itself towards itself, and then Fc2 will be the resultant force by Q2 over Q0. So these two forces are in opposite directions. So if the magnitude will be equal, in that case they produce an equilibrium point. Means C might be an equilibrium point if the forces are equal there. So C is also a point of equilibrium. Now, in which case B becomes equilibrium point and in which case C becomes equilibrium point, that I'll have to decide. So if the magnitude of Q1 is greater, in that case the force here Fb1 will be quite greater than Fb2 because the magnitude is greater and distance is also smaller compared to the distance of Q2 to Q0. So if Q1 is greater than Q2 in magnitude, in that case here Fb1 is quite greater than Fb2, so they not cancel each other at any points up to infinity. So force will not be zero here. So will not be an equilibrium point in the case of Q1 is greater than Q2. Similarly, if Q2 is greater than Q1, in that case C will not be an equilibrium point because why? The force applied by Q2 over Q0, that is Fc2, it must be greater than Fc1 because why? The distance is greater here. So what our conclusion is here? We conclude that B will be equilibrium point when Q2 is greater than Q1 in magnitude, and C will be equilibrium point when Q2 is smaller than Q1 in magnitude. So B is equals to equilibrium point. The condition is that when Q1, magnitude of Q1 is smaller than Q2, in that case B will be equilibrium point, and when magnitude of Q1 is greater than Q2, in that case C2 will be C will be equilibrium points. So you can get equilibrium points from here to infinity at each and every point. So here you can also get equilibrium points from here to infinity when your Q1 is smaller than Q2 in magnitude. So we notice here how to analyze qualitatively our equilibrium points. Now to check what is the value of our equilibrium point here. Suppose Q1 is greater than Q2. In that case, our C will be equilibrium point. So this distance is x and this distance is r. So force Fc1 is equals to Fc2. And what is the value of Fc1 here? The value of Fc1 is equals to Q1 Q0 by 4 pi epsilon naught, and this distance, you need this distance, that is r plus x whole square. Similarly, Fc2, value of Fc2 will be Q2 into Q0 by this square, that is Q2 Q0 by 4 pi epsilon naught x square. So what are you seeing here? Q0 cancels, 4 pi epsilon naught cancels. So what are you getting? X by r plus x is equals to Q2 by Q1. Again the ratio will be same. Sorry, let me try. X by r plus x is equals to Q2 by Q1. So we are getting this data here, that this distance ratio to this distance is equals to Q2 by Q1 under root. Means that here you can solve the value, you can solve this equation to get the value of x from here. So we can find where our equilibrium point lies to Q2. Similarly, if magnitude of Q1 is greater than Q2, then we get equilibrium points to this side at a distance x. Similarly, if our Q1 is smaller than Q2, in that case we get equilibrium points to this side of Q1 at a distance x. But the distance x will be calculated like this. So we have analyzed. Let me analyze some do some analysis based on equilibrium points that are roughly qualitative analysis. Suppose instead of two different magnitudes, I'm giving two similar magnitudes, but they are opposite in nature. So according to our conclusion, we can say that we don't have equilibrium points in between plus q and minus q. So we can say that we have equilibrium points to this side, we have equilibrium points to this side. But theoretically, before starting to derive equilibrium points, we need to do some qualitative analysis here. We have this point here, B, and we have this point here, C.
B is not visible. It's exactly on the spot.
It's exactly on this point.
Yeah, it's visible.
See, here B at a distance x from here. So, if the two charges are equal in magnitude, then our force here over this Q naught by this and this will be, suppose I assign this point as 1 and this point is 2. So force here at B by 1 is in this direction and force here that is at B2. So can convince yourself that these two forces will be equal or not? No, they will not be equal. Because why? Plus Q is here, minus Q is here. Both the charges have same magnitude, and the force produced between two equal charges at two different distances are never become equal in the magnitude. So FB2 and B1 never become equal to any distance up to infinity. So we have no equilibrium point here. Similarly, make the same analysis to C. It is at a distance x from plus Q and minus Q have a distance r plus x over a test charge kept here, C. So the forces by plus Q is in this direction, that is F C1, and force by minus Q over this Q naught is in this direction, that is F C2. So again the forces are opposite in nature, but due to the equal magnitudes of the charges at two different positions, the forces are not equal. So these two are same charge, this charge and this charge and this distance, this and this over this distance. Let's see. FC1 is equals to Q naught by 4 pi epsilon naught x square. FC2 Q naught by 4 pi epsilon naught r plus x whole square. So see, if the product of charges are same in both the forces and the distance are different, they never become equal. So they never cancel each other. Having their direction opposite to each other, they will not cancel each other because their magnitudes are not equal. So from here to infinity, you don't get any point that is an equilibrium point. So what's our conclusion here? We can say and we can convince ourselves that we get equilibrium point at infinity only when the charges are equal in magnitude. When the charges are equal in magnitude, remember here, when the charges are equal in magnitude and they have different signs, the equilibrium point exists at infinity. See, remember here, this is a critical point to note here that this is a critical point here that if the charges have same in magnitude but different in nature, one is positive, one is negative, then you don't get equilibrium point anywhere, either in between, either to this side, that side. We don't get any equilibrium point anywhere in this setup of charges. So we convince ourselves that we get an equilibrium point at infinity. But if the charges are same in magnitude and even in nature both, then we must have equilibrium point in between them. That I had already discussed. How we get equilibrium point at infinity? Check it. Suppose I take a point at infinity. See, if r is very, very greater than x, no, sorry, I have written wrong. X is very, very greater than r. In that case, if x is very, very greater than r, in that case, force either on B, either on C. So Fc1 is equals to Fc2. Check it. 1 by 4 pi epsilon naught q naught by x squared. 1 by 4 pi epsilon naught q naught by r plus x. I need to write it correct. Just pick it. See this here. I said earlier that the condition is that x is greater and greater than r, means x is very, very greater than r. In that case, suppose I'm taking in that direction. So Fc1 is equals to Fc2. So the force Fc1 will be this to this. That is, suppose q naught by x squared or 1 by 4 pi epsilon. Similarly here 1 by 4 pi epsilon or q naught by r plus x whole square. So r is very, very smaller than x. Then we can neglect it and we get almost these two forces equal. That's why we say that we get infinity as our equilibrium points when the charges are equal in magnitude and opposite in nature. But if the charges are same in nature, our equilibrium point lies in between them. So equilibrium points have been discussed. Now I'm moving on next type of numerical section, that is superposition principle of the forces. As we know, electrostatic force or Coulomb force is a vector, so we cannot write it add it like a scalar. So we need vector analysis to add it anywhere. Suppose a charge is experiencing 2 or 3 forces by any other charges. So the resultant force at that charge will be the superposition of all the 3 forces. But the superposition here is based on vector analysis, not the scalar analysis. Suppose I'm taking this. See, this is the equilateral triangle. So I have put three charges at three corners of this equilateral triangle, and all the sides are equal. So I can assign the sides as R, R, and R. Now, our job is to find the force at Q2 by this Q1 and Q3. So, as we know, all the three charges are positive. See here, we have an equilateral triangle here. We have an equilateral triangle here, and there are three charges on each corner of the equilateral triangle. There are Q1, Q2, and Q3. So here, all the three sides are equal. All the three sides are equal. So what I conclude here, I'm concluding that the force over Q2 by Q1 and Q3 mic is disturbing me. The force over Q2 by Q1 and Q3 is the resultant force of these two forces. So I'll have to find the resultant of these two forces. So force over Q2 by Q1 is repulsive, so it will be in this direction. Force over Q2 by Q3 is also repulsive, so it will be in this direction. And now our job is to add these two forces vectorally to find the resultant force. For that, we need an angle theta. So theta is the angle between this and this. And as we know, it's an equilateral triangle, so it will be 60 degrees. So this is also 60 degrees. So our job is force resultant force over 2 is equals to, that is F21 plus F23, and the value of this is equals to F21 magnitude squared plus F23 magnitude squared plus 2F1 F21 magnitude into F23 into cos theta. So this is our resultant force on Q2. Actually, this is the addition of these two forces, but the forces are vector quantities, so addition will be by the help of vector, not a scalar. So we have to find the addition of these two forces by the parallelogram law. What happened?
Nothing.
See this. This is the superposition, means the force, the resultant force follows the additive property, but addition must be based on the vector. So this, suppose I'm bringing some change in this question to get a new type of question. That will be Q2. And here I'm assigning minus Q3. See, now I'm telling you to find the force at Q2 by Q1 and Q3. So again, this will be repulsive, F21. But be careful this time. F over Q2 by Q3 is not repulsive this time. It will be attractive. So it's in this. Why it is attractive? Because it is positive, it is negative. So the resultant of these two forces, suppose it's in this direction, that will be the resultant force on charge Q2. That will be the resultant force on the charge Q2. And this time, this angle will be 180 minus theta. So again, F R2 is equals to F21 plus F23, and this time our resultant force, we apply parallelogram law by this angle, no, by this angle. We have to use this angle to find the resultant force between this and this. F23 magnitude square. See this time we are getting this. So if there are negative in charge, so we'll have to determine the traction and repulsion of the charges to find the resultant force. Actually, force follows this addition properties, that is called superposition principle. Now see another question based on this type of superposition principle of force.
It's 26 minutes.
Let it to go.
Speak up.
This time I have placed 4 charges Q1, Q2, Q3, Q4 on the corners of a square which have side A, and A. So actually these are not Q, these are A. Now again my question is that to find the force over Q2 by all the 3 charges. So we have to follow the same procedure that we have done there. In triangle, in equilateral triangle, whatever we have done there, we have to do here the same analysis, same way to find the force over Q2. Suppose see here, force by Q1 over Q2 is repulsive, so it will be in this direction. Force by Q3 over Q2 is also repulsive, and it will be in this direction. And force by Q4 over Q2 is also repulsive, and it will be in this direction. So this time you'll have to add these 3 forces to get resultant force. And it's quite complex here, because why? Those of you are not aware of vector analysis, vector for multiple vectors, vector addition for several vectors, are not able to solve this question, because why? This is not ordinary 2 vector to add, here 3 vectors. So we'll have to follow the component process. But the process is same. So for the component process, we need 3 angles. This, see, these are 3 forces. So I'm erasing this part of the figure, the derivation of the force.
We need to consider the part.
Suppose this is my x-axis and this is my y-axis. F21, F23, and F24. See, to find the vector addition by the component process, we need 2 axes, x-axis and y-axis. So I have taken x-axis along F21 according to symmetry and y-axis opposite to F23 according to symmetry of the figure. This third force, F24, is in this direction. come here to find, whenever we have vectors more than 2 or 3 and we need to add or subtract, then we'll have to follow this component process. I call it component process. It's quite easier. We can add or subtract 100 of vectors by this process. See here. For this, we need to find x component of first vector f21. That is magnitude of f21 into the angle made by f21 over cos x-axis. That is cos 0. f23. That is f23 cos. This will be the angle of f23. That is cos 180. X component of f24. That is f24. That is cos. This will be the angle made by f24 with the x-axis. That is cos.
There was not 180, there was 270.
Oh, sorry. Yes, that was 270.
Or you can go through this side.
Yes, I'm going. Cos
Cos 90.
something. It's actually diagonal. So 360 minus 45. See why I have taken these things. In component process, we'll have to find the x component of first vector, similarly x component of second vector, and similarly x component of third vector. So to find the x component of first vector, I need the angle made by first vector with the x-axis. So f21 is along x-axis, so f21 is along the x-axis, so it make angle 0. So I'm taking f21 cos 0 degree. Actually, this is the magnitude of force of this vector. This is the magnitude, not its vector form. It is in magnitude. f21 into cos 0 degree. Similarly, x component of f23. f23 is here. So in her you can calculate angle from this side, but no, that's a mistake. That's an error. We'll have to always calculate the angle from the anti-clockwise direction from x-axis to calculate the components. So f23 makes an angle of 270 degree from positive side of x-axis. So f23 into cos 270. Similarly, this is making this angle. So this angle will be actually f24 is along the diagonal of our square, of our figure. f24 is along the diagonal of our setup of the question. So diagonal makes an angle of 45 degree with the corners. So cos 360 cos, so x component of f24 is equals to cos 360 minus 45 degree. Understood? This is our x component. Now we have the total x component. That is f21 cos 0 plus f23 cos 270, and further let me to add f24 cos 360 minus 45, that will be 10.5 315 degree. Is it visible clearly?
Yes.
So we have total x component at this point will be this. Our job ends here. Now we'll have to find y component of each and every vector and then total y component of all the three vectors to add. Similarly, we can find y component. Y component of f21. That is f21 sine 0.